Welcome back from the break. I'm very glad that you could join me again. We're going to go on with the chemical equilibrium in acid-base reactions. And if you can remember, before the break, we started to look at auto-ionization of water. We said auto-ionization of water is where water reacts with water and a proton is donated from the acid and accepted by the base. We call that auto-ionization, but another name for it is autoprotolysis, meaning auto comes from water with itself and protolysis comes from transfer of a proton. Back to the auto-ionization of water, we ended off saying that Kw, which is the ionization constant for water, remember it is a constant and it's only applicable at 25 degrees Celsius. As soon as this temperature changes, we cannot use that as a constant. The constant actually says that for a neutral substance like water, we will have the hydronium ion concentration is equal to the hydroxide concentration, and that is equal to 1 times 10 to the power minus 7. It's a very, very low value, but that is because water wants to stay in molecule form instead of being in ionic form. If there's a decrease in the hydronium ion concentration, there will be an increase in the hydroxide ion concentration. What do I actually say here? I actually say if the hydronium ion concentration times the hydroxide ion concentration is at 25 degrees and it has a constant Kw value of 1 times 10 to the power minus 14, it basically means that if the hydronium ion concentration will increase, for Kw to remain that value at 25 degrees Celsius, it actually means that when the hydronium ion concentration increases, the hydroxide ion concentration will decrease. And we also say then, if there's an increase in if there's a decrease in the hydronium ion concentration, then we will have an increase in the hydroxide ion concentration. And this, again, can only happen at 25 degrees Celsius because Kw is only affected by temperature. So this is only if the temperature remains 25 degrees Celsius. Kw, as we know, like Kc, is only affected by temperature. I've said it so many times, I think you now know that. And because Kw is only affected by temperature, if the temperature is not changed, then it means Kw is equal to 1 times 10 to the power minus 14, meaning an increase in the one ion solution concentration will mean a decrease in the other ion solution, ion concentration. So the Kw means that hydronium ion concentration times your hydroxide ion concentration will have that constant. If the hydronium ion concentration increases, the hydroxide ion concentration will decrease and the other way around. And because of that, we can actually say that your hydroxide ion concentration is inversely proportional to your hydronium ion concentration. Or you can always say it the other way around. If you write it out, you actually say hydroxide ion concentration is inversely proportional to the hydronium ion concentration. Right, now if we look at the relationship, if it's shown on graphically, we can see that the hydronium ion concentration will decrease as the hydroxide ion concentration will increase by the same proportion. And as I said, I can also write it like this. Hydronium ion concentration is inversely proportional to the hydroxide ion concentration. But again, remember, you can only make that statement for Kc then to be, for Kw then to be that value, 25 degrees Celsius. So to recap again, if you have a neutral solution, your hydroxide ion concentration is equal to your hydronium ion concentration. When you have an acidic solution, you know that we know something is acidic because of the hydronium ion concentration or the hydronium ions in the solution. So when you look at an acidic solution, the hydronium ions in the solution will be more than the hydroxide ions. And for a basic solution, we will have more hydroxide ions in the solution compared to the hydronium ions in solution. Now, this needs to be kept in mind as we're going to look at these changes all along. What you should just keep in mind is for all of these, the value at 25 degrees should be 1 times 10 to the power minus 14. And this brings us to the next concept. Again, we've spoken about this before, strong acid. When we think about a strong acid, we should think about an acid that ionizes completely. To state it differently, if I, for instance, look at hydrochloric acid, which is a strong acid, and I'm just going to use an S and A as abbreviation, when it is mixed with water, it will then ionize into chloride ions and hydronium ions in the water solution. So when we say it completely ionizes, it basically means that the forward reaction is favored. So our equilibrium actually lies more to the right. So at any point, again, our hydrochloric acid will not be in molecular form. Hydrochloric acid will rather be in an ionic form. So when the forward reaction is favored, very few molecules of the hydrochloric acid that we will have, and we will have a lot of chloride ions and hydronium ions in the solution. And that is also how we know a strong acid, that a strong acid always favors the forward reaction. A strong acid always wants to be in ionic than molecular form. If we look at the hydrochloric acid then, being a strong acid, being mixed with water, which is a base but really a very weak base, all the hydrochloric acid will try to convert into hydronium ions and chloride ions. And if we go look at our Kc value, and in this case that Kc value is now called Ka because it is now referring to an acid. So the equilibrium constant for an acid is also called the ionization constant for the acid, will then be the same as any equilibrium constant that we called Kc before. Remember, if you think in terms of Kc, you also now know Kw, and I've just introduced to you Ka. Just remember, an equilibrium constant is only affected by temperature. So if we go back to the Ka value here of the hydrochloric acid, we will see that all of our hydrochloric acid will convert into hydronium ions and chloride ions. That means it will have a very high concentration of hydronium ions. High concentration of hydronium ions mean that for a strong acid, you will have your concentration of your hydronium ion in a range of 1 times 10 to the power 0 up to 1 times 10 to the power minus 2 moles per decimeters cubed. The Ka value, which is the ionization constant value, will then also be high, and that comes from the high concentration of hydronium ions. And for that reason, you should know that a strong acid has got a very high Ka value. And a high Ka value simply means that it's bigger than 1. When we look at a strong base is a base that dissociates completely. What does that mean? It basically means that the forward reaction is favored. If sodium hydroxide should decide to be in molecular form or in ionic form, it will all rather dissociate and be in ionic form. So at equilibrium, you will have almost all of it will be ions, hydroxide ions and sodium ions in the solution. And because this is a strong base, if you go look at all the sodium hydroxide converted into ions, it basically means that my hydroxide ion concentration for a strong base is very high. And you will see that the little strong base now slipped in here, and it made now a dissociation constant, as we call it, and we call it Kb. So just to remind you, we've got Kc for chemical equilibrium of any reaction. Then we have Kw for autoionization of water. Then we have the equilibrium constant Ka for acids, and the equilibrium constant Kb for bases. So when we have a strong base, we will have a high concentration of hydroxide ions in solution. The high concentration of hydroxide ions can be anything between, if you go look at OH minus times hydronium ion concentration, that will be equal to 1 times 10 to the power minus 14 for our Kw value. If you go look at your high concentration of hydronium ions, it will have a very low concentration of hydronium ions. Sorry, it's a high concentration of hydroxyl ions and a low concentration of hydronium ions. And your hydronium ion concentration will be in that range. As I said before, the Kb is the dissociation constant of a base, and for a strong base, we will have a high Kb value, or we can say the Kb value is bigger than 1. First question there, calculate the hydroxide ion concentration of a hydrochloric acid solution. That is the hydroxide ion solution. Now we know that for all solutions, we have hydronium ions as well as hydroxide ions in solution. But what we say now is calculate the hydroxide ion solution if hydrochloric acid solution has got a concentration of that. Now hydrochloric acid is a strong acid, which means it will completely ionize and form hydronium ions in concentration. And we also know then that if hydrochloric acid has got a concentration of 1 times 10 to the power minus 3, it means that the concentration of my hydronium ions is equal to 1 times 10 to the power of minus 3. And we can only do this if we have a strong acid or a strong base. But for a strong base, it will be equal to the hydroxide ion concentration. We go on, we make the statement there that all the hydrochloric acid in concentration will now be equal to the hydronium ions in the solution. That brings us to the Kw, because we want to work out the hydroxide ion concentration. We have that, and we know this is a constant. We can now use the Kw. Remember we said with Kw remain constant. Your hydronium ion concentration and your hydroxide ion concentration is inversely proportional. So we can then say that if that is all equal to 1 times 10 to the power minus 14, my hydroxide ion concentration is 1 times 10 to the power minus 11 moles per decimeters cubed.